Perfect. So, first thing for this morning is this is a plenary talk from Elena, and then after this hour, we're going to split between this group.
Thank you very much for the introduction. Can everyone hear me? Yeah, okay, good. So today I'm going to talk about partial Markov categories, as the title says. And this is recent joint work with Mario. Since I have an hour, I will spend some time with motivation and some background and related work. Okay. So what was the motivation for this work? We wanted to find what's a minimal algebraic structure to express updates on a model, on a stochastic model. And we already know that Markov categories are very good to express probabilistic processes. So we're going to start from there. But then we need to add some more expressivity, and that is going to be the partial part. So we're going to allow our morphisms to be partial.
So the screen isn't shared on the
the screen is, thanks, Cole.
Thanks.
Okay, can you see it now?
Yes.
Thanks. Okay, so what we're saying, right. So we need to add partiality to. So I'm going to recap what copy-discard categories are, what Markov categories are, and then Cartesian restriction categories that are a framework for partial computations, and then we put them together to get partial Markov categories. Okay, I guess this is just so that everyone knows, but I think everyone already knows. String diagrams, I'm going to use string diagrams for symmetric monoidal categories. So we put boxes in parallel and in sequence to monoidal product and composition. And what are the examples or famous examples? Well, sets and functions. But more relevant to this talk are going to be the category of sets and partial functions, sets and stochastic functions. I will introduce them in a bit more detail later. They're actually used. And then relations and partial stochastic functions that are going to be the simplest main example of partial Markov categories. Okay, all these are Kleisli over set. So they all share this structure, which is they have every object has a commutative comonoid structure, so we can copy resources, and we can do so in a uniform way. So copying two resources at the same time is the same as copying one and then copying the other. Same with discarding. I think you've seen this during Probably not. Right. Anyway, yeah, that's the definition. Okay, so once you have this copy-discard structure, you can characterize some of the maps of your category. Some of them, they can be copied. So not only the resource, but the morphism can be copied, and that's going to be a deterministic morphism, right? Because if I can do the morphism, copy the output, and that's the same as copying the input and then doing the morphism, it means that it doesn't matter if I do the morphism twice or I just copy the output. Characterizes deterministic morphism. And total maps are the ones that can be parted. So if we go to our examples, sets, that all the maps can be copied and discarded. In fact, all the maps are both deterministic and total. But then in partial functions, as we might expect, all the morphisms are deterministic, but not necessarily total. In fact, they might be partial. In the classic category of the distribution monad, not all the morphisms are deterministic, but they are all total. While in relations and in subdistributions, not all the morphisms are either total or deterministic. So in fact, we can characterize Cartesian categories as the ones where all the morphisms are total and deterministic. So we're going to see what happens when we drop one of these two. We're going to start with Markov categories. So take a Cartesian category, the copy discard structure, but we drop the determinism, then what we get is a Markov category, right? So as I was saying at the beginning, Markov categories are good to express probabilistic processes like throwing a coin or clouds or things like that. And okay, so we want to be able to express something that is not deterministic. We have our copy discard structure. We ask that all the morphisms are. Then we ask that all of them are deterministic. And if we also want to be able to condition, if we're going to produce two outputs, and we want to say, okay, maybe one of them is produced before the other, then we ask for conditionals, which is, if I have a process F that produces, let's say, A, and I want to say, okay, but maybe A is produced before B, then I can split F to produce first A with M, the marginal, and then produce B with the. As it to the partial setting is not straightforward. Oh, okay.
Hold that one.
No, yeah. I can. Is it better now? Yeah, I guess maybe. Okay, yeah, sorry about that. Okay, we have Markov categories. What's the example? Finitary distributions, let's say the simplest examples. What's a finitary distribution? It's a function that assigns to each element of the set a probability. And we ask that the support is finite. So this probability is non-zero for a finite amount of elements. And also the probability mass is 1. A morphism in the Kleisli category of the distribution monad. So this defines the monad and it's monoidal, everyone is happy. So we can do the Kleisli category, and it's also a copy discard category. And we think of morphisms there as stochastic channels. So we write f of A given X as, and we think of it as the probability of A given that X is the input. Composition is just composition, is like, if you imagine that F happens and then G happens, the probability that B happens given that X was the input, you just sum over all the possible A's that could have given B as output. Okay. Any questions so far? Okay. So this category has conditionals, which is nice. And how are they defined? Well, the marginal is what you would expect. So if you have your channel F that produces an A and a B, if you want to know what's the probability that A is produced, you just sum over all the possible b's. And that corresponds to discarding the b wire. And what are conditionals? Well, it's just f, but rescaled by the marginal when the marginal is not 0, because you cannot divide by 0, right? So when the marginal is 0, you can just pick any distribution on B and put it here. So this shows that conditionals are not unique, and in fact they cannot be, because otherwise your Markov category collapses, which is bad. But maybe, I don't know, maybe it's not so desirable that there is this freedom of choice in the conditionals. And we will see at the end of the talk how in partial Markov categories, sometimes you can characterize the nicest conditionals. Okay, so since all the morphisms in Markov categories are total, we can show that the marginals are actually always the ones as in the Kleisli of distributions. So the marginals are always obtained by discarding one of the outputs. And yeah, that's easy to see. So if I have my f, I condition, and then I can just discard the conditional because it's total. So I obtain my marginal. Okay, so we want to keep this property when we move to the partial setting, so just keep it in mind. In Markov categories, if you have conditionals, one thing you can do is express bias inversions. This is known. And they are a particular case of conditionals. So if I have a prior distribution, sigma, on B, and I have a channel from B to A, then I can invert my channel G with respect to sigma and obtain this G dagger sigma from A to B. And that corresponds to doing a bias formula. Yeah. Okay, so that was it with Markov categories. So if there are any questions about that part, please, you can ask now. I guess no? Okay. Okay, so now we'll move to the part, oh yes.
You talked about how discarding, like you can only discard if it's total, and totalness came up in the marginalization.
Yes.
Is that going to be important?
Yes.
Okay.
Okay.
I was confused by like why we can't discard if they like why can't we discard partial functions?
You cannot because oh right.
Why can't we discard partial functions?
So why cannot partial functions be discarded? So if you imagine, I'm going to talk about that more later, but if you imagine the discard being, it just gives you the domain of definition, right? In partial functions, it gives you what are the elements in A that have some image. And then if you do F and then discard, that gives you all the elements in A that have some image along F. So it gives you the domain of F.
Partial functions can change the domain of definition.
Yeah. Okay, so yeah, in fact, now we're going to see Cartesian restriction categories that are, well, I guess a well-known categorical framework for partial computations, like, I don't know, computing X, or checking a quality of two inputs, or non-terminating computations, stuff like that. Okay, so the categorical structure that we're going to ask is, again, copy and discard, a co-commutative comonoid. Everyone is happy. And then we're going to drop totality, right? But still we ask a determinism because we're still in the deterministic world. And what's the main example? Partial functions. So objects are sets, and morphisms from A to B are functions from A to B plus 1. So if the computation f fails, you're just going to return the 1. So bottom, we write it bottom. And we interpret it as, yeah, the computation just failed. Composition, well, just composition of functions, but failure, so if I do f and then g, I can fail when either f fails or and g, yeah, or g fails, right? Okay. Then, as James was asking before, this non-totality allows us to express predicates and domains. So a morphism A to 1 in partial functions is a predicate because it gives us a subset of the domain A, right? So if we have a morphism from A to B, and then we discard the output, that gives us the elements of A on which f is defined. And in partial functions or in Cartesian restriction categories in general, every morphism has a domain. In fact, we can copy because everything is deterministic. And so we can write f as its domain and itself. This structure induces a preorder on the morphisms. And it's called restriction preorder because f is less or equal than g if f is a restriction of g to its domain. So this equality here says that f is equal to g only on the inputs on where f is defined. Okay. But partial functions also have an additional piece of structure, which is this equality check. And it behaves nicely with the copy structure. So if we copy and then check equality, that's the same as doing nothing. And also this other way. So if we first check equality and then copy, we can do it in the other order as long as they're connected along only one wire. And yeah, so this structure is called the one of a discrete Cartesian restriction category. So we have copy discard, every morphism is deterministic. Not every morphism is total, not necessarily at least. And then we add this comparator structure and we ask that it behaves like an equality check. It satisfies this partial Frobenius structure, if you know about that. So it's like Frobenius, but there's no unit. Oh, right, yeah, the prototypical example is again partial functions, I guess. Okay, any questions so far? I guess now we can move to partial Markov categories. So we put these two together. And yeah, and why do we do that? So I was saying at the beginning that we wanted to do observations and updates on observations. But why do we come to this structure? So if we want to update a model on an observation, then what we want to do is restrict the model f to all the scenarios that are compatible with our observation. So we kind of want to express in our language a constraint. But a constraint cannot be a total computation, right? Otherwise, it wouldn't be a constraint. So we want to express probability, so we use something like Markov categories, but also we want to express partial computation. So something like Cartesian restriction categories. So yeah, that's what we're going to do, put them together. But there's a subtlety here. So we will ask for conditionals, but we want also to keep some of the nice properties that conditionals have in Markov categories. For example, that the marginal is precisely discarding one of the outputs, and that is not necessarily true if you drop totality of your morphisms. So one thing we could do is ask that all the conditionals are total, but that is too strong, because that is not even true in the simplest example. So we're going to ask that conditionals are quasi-total. And what does that mean? That means that the domain of definition, or well, better, the probability of failure of a morphism is deterministic, so it can be copied. And intuitively, that means that F has a domain of definition. So there are some of the inputs in which the channel is defined and gives a normal probability distribution, and some of the inputs in which it just fails, for sure. Okay, so with these considerations, we end up with partial Markov categories. So we have a copy-discard structure, and the morphisms might be non-deterministic and non-total. Okay. And then we ask for conditionals. So it's the same equation as for Markov categories. So we have the same splitting, one happens before the other. But also we ask that the conditional needs to be a quasi-total morphism, so that we recover some of the nice properties. In particular, we recover that the marginal is F discarding one of the outputs. What's the canonical example is the Kleisli category of the finitary subdistribution monad. So what's a subdistribution is the same as a distribution, but the total probability mass is at most 1. So it can be less than 1, and the remaining probability mass is the probability of failure. So morphism, let's say from X to A, in this Kleisli category, if I evaluate on A given the input X, it's going to give me, again, the probability of A given X. But then also, there is a probability of failure. So given an X, this channel might fail with some probability. Composition is very similar to composition in distributions, but for the failure, the composition fails when either F fails or F succeeds and then G fails. So that's, let's say, the simplest example, but every time that you have a Markov category with conditionals and coproducts, you can do the maybe monad on this Markov category. If this maybe monad satisfies some ugly technical conditions, then the Kleisli category of the maybe monad is a partial Markov category. So in particular, subdistributions on standard Borel spaces is partial Markov. Okay, so in this setting, we have the structure to talk about predicates and domains in the same way we were talking about them in partial functions, but this time the predicates are not like classical predicates, because for every element in A, I have a probability that A is true. And when these predicates can be copied, so let's say Q is the same as copying and then doing Q, then this Q is a classical predicate. So instead of having a probability, I just have, so all the probabilities are either 0 or 1, right? So it's deterministic. And we can see the quasi-total condition in this slide. So the probability of failure of a morphism, when it can be copied, so when this predicate is deterministic, it means that Yeah, it means that F has a domain of definition, as I was saying before. So either F certainly fails, or it gives a total distribution. Okay, any questions about this before conditionals? Yes. Oh, yes. So what is an F that doesn't satisfy this equation? So let's say that my domain is, I don't know, 2, the 2-element set. And if I receive 1, I fail with probability 1/2, and I succeed with probability 1/2. That is non-total, because the probability of failure depends on. Yeah, because there is a probability of failure that is non-zero and non-1. Yeah. Okay. Thank you. Okay. So subdistributions also have conditionals, and they are quasi-total. The marginals are the same as in the total case. So I just discard one of the outputs. But for the conditionals, we can do something, let's say, nicer. So when the marginal is non-zero, we do the usual thing. So we renormalize our channel F. But when it's 0, we have, let's say, a canonical choice, which is we just fail, right? Because if you receive an input that you did not expect, you can come up with the distribution, a random distribution, like in Markov categories, or like or you can just say I don't know, and that's when you choose to just return failure. But it's not the only choice, but it looks like the canonical one, and we'll see how it is canonical later. Okay, so the structure of conditionals allows to do Bayes inversions in the same way as in Markov categories. So yeah, Bayes inversions are just a particular case of conditionals. Yeah. But also, we can do normalizations. So if I have a channel, and this channel is not total, so sometimes it fails with some probability, I would like to look at the renormalization of that. So I would like to divide by its probability of failure, and that is also a particular case of quasi-total conditionals. So yeah, if I have F and I condition on the monoidal unit, I obtain the marginal, which is F discarded, so the domain of F. And the conditional is normalization, because it's quasi-total. Any questions about that? Yeah, so I don't know. It feels like you should be able to, but I'm not sure. So later I will say something more about this. Thank you for the question. Okay, so subdistributions also have equality checks, which is nice, and they also behave nicely with the copy structure in the same way they did in partial functions. So we can define discrete partial Markov categories, which are partial Markov categories with an additional piece of structure, which is the comparator. And this comparator behaves like an equality check. Yeah, we can keep the same intuitions as in partial functions. And with this structure, we can prove a synthetic Bayes theorem. So what does this say? If we have a prior distribution on X, and we observe a deterministic point in A through a channel, C from X to A, then we should update our prior sigma proportionally to the bias inversion of C evaluated on A. Okay, so this corresponds to this equation in string diagrams. And why is that Bayes' theorem? So this is the usual formula. And we can find all the factors in the string diagram. So probability of X given A, that is this one, right? I'm computing X given that A happened. Then the probability of A given X, this is this part here. So I have A given X times the probability of X, so this sigma. And then this normalization factor is just this color here. And the proof is neat because we use exactly the axioms that we asked. So if we start from the left-hand side, we use conditionals to invert the channel. Then we use the Frobenius axioms here. And then we can copy our observation because it's deterministic. And we obtain the right-hand side. Other things that we can do with these updates and the grid structure is express Peirce and Jeffreys updates. I don't know if you've ever heard of them, but there's apparently some disagreement on how you should update, or at least there are two ways of updating. And somehow writing them formally in a category clarifies why they're different and how. So if we have evidence, a type of evidence that is a predicate, then we can update according to Pearl. And how do we do that? We just reduce using a Bayes theorem. And our posterior is this updated prior, and the one that comes from Bayes. But on the other hand, if we have evidence that is a state, not a predicate, so it's just a distribution over, it's just a distribution, then what we do is do again the Bayes inversion, and then evaluating this Bayes inversion on our evidence. And when the evidence is deterministic, so when we are observing just a point, then these two things coincide. This was shown by Jacobs already for distributions, but you can prove this in any discrete partial Markov. So I don't know, that's nice. Any questions? Okay. So I've been talking about observations and how you need the discrete structure to do that. But what happens if you don't have this discrete structure? Well, good news. You can still do exact observations. If you have your Markov category, I forgot to say with conditionals. So you need conditionals. Have your Markov category with conditionals. You can construct freely a partial Markov category by adding exact observations. And what does that mean? So I take all the deterministic states in my base Markov category, and for each of them, I add a predicate, and I think of it as observing A. And then I ask that these predicates satisfy this equation here, and we think of this equation as really the Frobenius, a consequence of the Frobenius axiom. And we can, let's say, think of them in this way, because in fact, this construction embeds faithfully into the free partial Frobenius over your base Markov category. Okay, but now we have added things freely. So we don't know, in principle, we don't know how to compute with them. But we can show that both conditionals and normalizations are computed just by staying in C. So first, I have a normal form for all the morphisms in this construction, and this normal form is computed by induction, and it gives us the normalization of the channels. So I have a way for every channel to compute its normalization, and once I have the normalizations, I can compute conditionals. So this maybe answers somehow your questions from before. So if I take the conditional of the normalization of f, that's the same as a conditional of f. So I can do, yeah, I can do everything I need to do in this really generated category. Okay, I don't know why I always lose my audience here. So if you have questions, please ask. Yes.
Okay, I'll ask a really simple question then. Is a deterministic state of A just a point of A? Is that what I'm supposed to be thinking you're adding observations for?
Yes.
Okay, I thought it might have somehow become a little more at some point. Thanks.
Yeah. That's a good intuition, thanks. Oh, right, I forget. So the question was, should I think about deterministic states as points in A? Yes, and the answer is yes. Thank you for the question. Okay. Okay, so now the promise from before was, okay, some conditionals look nicer, but how nicer? Like, why are they nicer? And the answer is going to be because they're minimal in some sense. So if you remember the restriction preorder from Cartesian restriction categories, we can do a somehow similar thing here. So we say that f is less or equal than g when f is the same as g on the domain of f. But this is not a preorder in general, because reflexivity corresponds to quasi-totality. So it is a preorder, but only on quasi-total morphisms. But that's good enough, because our conditionals are quasi-total. So when our partial Markov category has minimal conditionals, we have a way of choosing a canonical one. And luckily, that happens in subdistributions. So if we look at all the conditionals in subdistributions, they are either, so yeah, when the marginal is not 0, then we just renormalize our channel, good. But then when it is 0, we can put whatever subdistribution, right? So yeah, but so when I don't know, when I receive an observation or when I receive an input that I didn't expect, I can choose what to do. But the minimal choice, but let's say, as I was saying before, the minimal choice or the canonical choice would be to say, I didn't expect this, so my channel should fail. And in fact, our subdistribution, the subdistribution that is somehow minimal, well, minimal in that sense, is the one that fails whenever the marginal is 0. So I just fail on unexpected observations. Okay. Summarize. We started from Cartesian categories. We dropped totality and to obtain Markov categories and Markov categories with conditionals. Then instead, if we drop determinism. Instead, if we drop totality, we obtain Cartesian restriction categories and discrete Cartesian restriction categories, and then we can put them together to obtain partial Markov and discrete partial Markov categories. Okay, so I have a final fun part, but if there are any questions so far, feel free to ask. Oh, sorry, I didn't see you.
Just because it's called discrete partial Markov, is that related to discrete distributions like only over finite sets?
So the name comes from discrete Cartesian restriction categories, but in fact, even the Kleiseli category of the subjury monad also has a discrete structure. So I don't know.
But will it work on like the Gaussian distribution over R? I can use distributions over continuous.
Yeah. You do have a comparator there. You have the equality check. Then it does create some problems with checking equality with 0, so weird things happen. But yeah, there is that structure. But when it doesn't behave as you wanted, you can always add it freely. Yes?
Fun question. Where does the where is that coming from?
So we have a bottom element in here, where whenever your channels can fail, then the bottom element represents failure. Is that your question?
Right. I was trying to think about like. Classification in the machine learning. Like.
Yeah, I'm not sure. So, okay, I should repeat the question. Okay.
Partial functions as pointed sets, and bottom is that point.
I don't know interpretation.
So it can just be any.
It's the I don't know interpretation, not the choose random.
Explicit.
Okay.
Yeah, okay, so the question was about the interpretation of the bottom element. Yes, and okay, I think you solved the question.
Yeah.
Good, thank you. Okay, so fun part.
Can I ask a question from
Yes.
online? Yes. Could you go back one slide? Yeah, so this equation right at the bottom where I take apart F into M and C. In the case where C is quasi-total, does it still follow that discarding the second output of F gives me M?
Yes.
Is that just a graphical proof?
Yeah, you need conditionals, but yes.
Okay, right, thanks.
Yeah, thank you. Okay, so fun part. Yes, oh no, there's another, sorry.
Two morphisms. Oh, thank you. If you have a copy map and then two more F and G in parallel, and you discard
The discarded morphism, oh, everything fails. Yes. Yes. Yeah. Failure is, yeah. When something fails in your diagram, everything fails. Yes, exactly. What?
Kill everything just because of.
Oh, no. But like.
If it completely fails.
What do you mean?
If it hits.
Yeah, like if you imagine running your morphism and then what you get is failure, then everything fails. So for the whole morphism, for the whole diagram to fail, you just need one of the components to fail. Yeah, on a given input, yes, yes. Yeah, thank you for the questions. Okay. Anything else? Good. So, okay. A fun example is Newcomb's problem. It's a bit confusing. Sometimes it's called Newcomb's paradox because, yeah, it's a bit confusing. So please ask questions yeah, if it's not clear. Okay. So you're an agent and you have two boxes in front of you. One of them is transparent and it contains, let's say, €1. The other one is opaque and it contains some amount, but you don't know exactly what's the amount, but you know that there is a predictor which is very accurate. So it is right in its predictions like 90% of the times. And this predictor is the one that decided how to fill the box, the opaque box. And if it predicts that you will take both boxes, then it will leave the box empty. While if it predicts that you will just take the opaque box, then it will put there, let's say, €10,000. So now you can choose whether to take both boxes or just the opaque box. What should you do? So there are various decision theories that try to answer this question. And let's say the two famous ones are causal decision theory and evidential decision theory. So if you decided today you're going to be a causal decision theorist, then you're going to ask yourself, what is the action that will cause the best case scenario? So you go to your utility table and you look at the rows and you say, well, I mean, if I two-box, I always get €1 extra in either cases. So I will two-box because in both scenarios, that's the best thing to do. But if you decide instead to be an evidential decision theorist, then you ask yourself, what is the action that will give me evidence that I am in the best case scenario? So you go to your utility table and you say, well, I mean, really, the most likely scenarios are along the diagonal. So I'm really choosing between these two. So I'd rather one box because then I get 10,000 and not just one. If we compare the two approaches, well, the evidential decision theorist in this case does better because on average, it gains more than the causal decision theorist. Okay, so this was not to convince you that evidential decision theory is better, but just to show that it's a bit tricky sometimes to reason with these problems. So it's good to have a formal way of doing it. And yeah, we did it for evidential decision theory. So causal decision theory, we won't look at it for now, but if you have Newcomb's problem and you want to solve it with evidential decision theory, then you can draw a string diagram like this in a partial Markov category. So you have your predictor and you have your agent, and you know that the predictor is right 90% of the times. So yeah, the prediction of the predictor is the same as the action of the agent with some noise in between. It's accurate, but not 100% accurate. And then, well, there's a utility function because at some point you get some euros out of this game. Okay, but how do we solve this? Well, we say the evidential decision theory is, you ask what is the action which would be evidence for the best case scenario. So you want to observe that you're doing one action. So you add an observation of a particular action, and then you can reduce your diagram. And then you just want to maximize the average of this state. So this uses the algebra of discrete partial Markov categories, which is okay. So to conclude, I hope I convinced you that partial Markov categories are good syntax for updating on observations. And then one thing that we would like to look at is these inequalities. It feels like they're pointing towards a bicategorical structure. Like if you know about Cartesian bicategories of relations, it sort of looks like there should be something there in that direction. But yeah, that's future work, so we'll see. Thank you. I'm happy to take any questions.
Thanks for.
Yeah, thanks for the nice talk. I was wondering if you have any examples of where the choice of conditional matters. Like, I mean, it's nice to have a canonical choice, but are there cases where like having that brings any advantage if you're doing the string diagram calculations and so on?
So for that to matter, for the choice of conditionals to matter, I guess you would need to take your conditional and plug it into something else that is not the marginal where it comes from.
And the classic reason for not caring about it is like in Bayesian inference is because you don't care about events with probability 0, right? So
yeah, exactly.
I'm wondering if this somehow surface, like if there's like a thing that happens here in this graphical calculus that where it matters, or if it's just like a.
Yeah, I haven't thought about that. Yeah, but see, you would need to use your conditional in a place where it shouldn't be somehow. Mario, maybe you have something to say?
I wanted to say that things like those, like, it doesn't matter which conditional you put, you can prove that. So in the cases you care about, you can prove that this is going to be the same. That kind of conditional.
Thank you for the wonderful talk here. As someone who is very algebra poisoned, I was unnerved by the lack of unit for the Frobenius structure, and it seems that that is coming from a failure of the multi-valuedness of these functions, just thinking Cartesianly. So I was wondering if these methods could be extended to, say, taking values in convex subsets of subdistributions, and whether you would get a full Frobenius structure if you did that.
Yeah, that is definitely something we want to look at. And somehow having a unit of the Frobenius structure would give you a uniform distribution, but you don't necessarily have them. So, but yeah, probably looking at examples a bit more, or models that are a bit more sophisticated, like convex sets of distributions or subdistributions. Yeah, would be very interesting. Yeah. Thanks.
Thanks.
Yeah.
This is sort of just a question about partial categories in general, or partial functions. When you're programming with partial functions, you can do like error handling, where you run a function, and if that function errors, you like catch the error and do something with it. Is there a way to model that categorically?
I guess instead of the maybe monad, you would need some exception monad or something. But I guess, or maybe you would need to change the monoidal structure, because you don't want that everything fails if somewhere you fail. So I'm not sure, maybe.
algebra for the monad.
Yeah. 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 So I will repeat what.
Okay.
So you can probably work with the algebras of monad. And yes.
Thanks for the talk. This is related to the first question. So is it true that the choice of a conditional would matter in the case of the Jeffreys update? Because in the Jeffreys update, the somehow distribution can change, and in particular, its domain could change. It's like where is non-zero could change.
That is true. So yeah, in fact, Jeffreys updates feels kind of weird to me.
Okay.
Yeah, I don't know. Yeah.
Great talk. And there is another theory which has partial morphisms and predicates, which is effectus theory. Do you know that one? And do you know how it relates to partial Markov categories? For example, is effectus with copiers a partial Markov category?
Yeah, so I know about that work. I haven't looked at exactly how they're related, but I know that effectuses have more structure. For example, they always have coproducts. And yeah, so there is, let's say, more structure to them. So I would suspect that every time that you have an effectus, maybe you can build a partial Markov category, but I haven't looked at the details of it. And let's say that this structure is more minimal. It's like the minimal thing you can have to prove something like bias. Thank you for the question, yeah.
I'm curious about non-sharp observations, and particularly whether you might be able to build on Paolo's work on divergence. Analyze sort of when your observations aren't sharp.
Yeah, so non-deterministic, right?
Yes.
Yeah. So if you don't have that, if your observation is not deterministic, you can still write this diagram. It's just that you cannot simplify it as something like this. Yeah, that is, yeah, probably. Thank you for the pointer. We will, yeah, there are so many interesting things to look at, and there is so much work around these things that, yeah. Thanks.
We're going to stop here because we're going to split now into two sessions, but let's thank Elena very much for us. Yes, we continue with probability in this room. Let me load up here. So in this room we have hidden Markov models and Bayes filter, and in the other room we have category theory applied to intent-based networking.
Realization that it's going to draw people. I didn't mean to make you feel guilty. Oh, you should shut me down. That's not true. Oh, I did. Cancel that.